Convolution is like taking one list of numbers, a signal, and sliding another list, a filter, across it, multiplying the overlapping pairs and adding the results. Imagine you have a row of Lego bricks, the signal, and a small hand-shaped stamp, the filter. You press the stamp on the bricks, count how many bricks it touches, then slide it one step and count again. Linear convolution is when the stamp never wraps around the end of the brick row. When the stamp reaches the far right, the parts that would stick out simply see nothing, zero. This gives a longer result because the stamp has to walk off the end. Circular convolution is like the brick row is a looped track. When the stamp moves past the last brick, it reappears at the first brick, so the ends are connected. The result has the same length as the original row, but some values are mixtures of pieces that wrapped around. Why do we need both? Linear convolution matches the real world for most filtering tasks, for example, a music equalizer. Circular convolution pops up when we use the discrete Fourier transform, DFT, because the DFT assumes the signal repeats forever, a natural circle. When we compute convolution with the DFT, we must either accept the circular version or change the data, so the circular version becomes the same as the linear one. Explanation: the math tells exactly how the sliding and adding works. Linear convolution of two finite length sequences x of n, length L sub x, and h of n, length L sub h, is defined as y of n equals the sum from k equals 0 to L sub h minus 1 of h of k times x of n minus k. For n equals 0, 1 L sub x plus L sub h minus 2. Where we treat x of m equals 0 for any index m outside 0 to L sub x minus 1. The sum slides the impulse response h over the signal x. The result length is L sub x plus L sub h minus 1. Circular convolution assumes the sequences are periodic with a common period, and the definition is y of n equals the sum from k equals 0 to n minus 1 of h of k times x of n minus k modulo n. For n equals 0, 1 n minus 1. Here the index n minus k modulo n means we wrap around when we go below 0. The values reappear from the other end. Derivation of the circular form comes from the property of the DFT. If x of k and h of k are the DFTs of x of n and h of n, both length n, then the pointwise product y of k equals x of k times h of k is the DFT of the circular convolution of the original sequences. This is why the DFT turns convolution into multiplication. The linear form can be derived from the same idea, but using a longer DFT size, 0 padding, so that the wrap around never mixes useful values. In that case, the circular convolution computed with the longer length is exactly the linear convolution. To make a circular convolution give the same answer as a linear one, we trick the DFT by adding zeros. 0 padding. Suppose x of n has length L sub x and h of n has length L sub h. Their linear convolution would need L equals L sub x plus L sub h minus 1 samples. We create new arrays x sub p of n and h sub p of n by appending zeros, so that each has length n greater than or equal to L. Commonly, we pick the next power of 2 for FFT efficiency. X sub p of n equals x of n for n between 0 and L sub x minus 1, and 0 for n from L sub x to n minus 1. Similarly, h sub p of n equals h of n for n between 0 and L sub h minus 1, and 0 for n from L sub h to n minus 1. The added zeros guarantee that when the circular shift wraps around it only sees zeros, so the wrap around does not change the sum. Periodic extension. After 0 padding, the sequences are considered periodic with period n, because the non-zero part fits entirely inside 1 period. The circular convolution of the padded sequences equals the linear convolution of the original ones. X of k equals FFT of size n of x sub p of n. H of k equals FFT of size n of h sub p of n. Y of k equals x of k times h of k. Y of n equals IFFT of size n of y of k. The first L samples of y of n are the desired linear convolution result. This conversion is the key that lets us use the fast FFT algorithm for ordinary non-circular filtering. The FFT, fast Fourier transform, is a clever way to compute the discrete Fourier transform in O of n log n time instead of O of n squared. Because the DFT turns convolution into multiplication, we can compute a convolution by 3 FFT steps. Transform both signals. Take the FFT of the zero-padded input x of n and the impulse response h of n. This moves each sequence from the time world to the frequency world, where each frequency bin tells how much of that sinusoid is present. Multiply pointwise. For every frequency bin k, multiply the two complex numbers. Y of k equals x of k times h of k. Multiplication here mixes the two spectra together, which is exactly what convolution does in the time domain. Transform back. Apply the inverse FFT, IFFT, to y of k. The result y of n is the convolution of the original sequences. Analogy: pretend you have two recipes, the sequences. Instead of mixing them ingredient by ingredient the slow O of n squared way, you first turn each recipe into a list of flavors. FFT, then you simply multiply matching flavors, fast pointwise multiplication, and finally you convert the combined flavor list back into a cooked dish. IFFT, the whole process is much quicker for long lists. When we zero pad to length n, often a power of 2, the 3 FFT IFFT calls each cost about n log 2 n operations, giving a total cost proportional to n log n, which is far less than the n squared operations required by the direct definition of convolution. When the signal we want to filter is very long, such as an audio recording lasting minutes, computing one giant FFT for the entire signal is wasteful because it requires a lot of memory and incurs the overhead of a huge transform. Overlap add, abbreviated OLS. Choose a block length L for the input, for example 1024 samples. The filter length is m, the FFT size is n equals L plus m minus 1, padded to a power of 2. For each block, 0 pad the block to length n, compute its FFT, multiply with the FFT of the filter, compute the inverse FFT, and keep the first L plus m minus 1 output samples. Because each block's output overlaps the next block's output by m minus 1 samples, we add the overlapping regions together to form the final continuous output. Overlap save, abbreviated OLS. Again, pick a block length L, often called n minus m plus 1 in this method. Pre-pad the filter to length n and compute its FFT once. For each block, take n consecutive input samples, but the first m minus 1 samples of the block are the last m minus 1 samples of the previous block. They are the overlap. Compute the FFT of the block, multiply with the filter's FFT, compute the inverse FFT, and save only the last L samples. The first m minus 1 samples are discarded because they are corrupted by circular wraparound. Concatenate the saved parts, no further addition is needed. Both methods produce exactly the same result as a straight linear convolution, but they keep the FFT size moderate, reuse the filter's FFT, and fit nicely into cache-friendly memory blocks. The choice between OLA and OLS often depends on ease of implementation and whether you prefer adding overlaps or discarding them. Direct time domain operations big O of n times m multiply each of the n input samples with each of the m filter taps. Memory minimal, just the two arrays. When it shines very short sequences, for example n and m less than 32, where the overhead of an FFT outweighs its speed. FFT-based single block operations big O of n log n for each FFT or IFFT, total roughly 3 n log n memory needs 3 arrays of length n plus temporary buffers. When it shines long sequences where n is large, especially when the same filter is applied to many blocks, filter FFT reused. Overlap add or overlap save operations big O of n log n for each block, but with a smaller n block size, and one filter FFT reused. Memory same as the FFT method plus a few extra buffers for overlap handling. When it shines streaming or real-time processing of very long signals, limited memory environments, hardware with fixed size caches. Latency, direct convolution can start producing output after the first few samples, while block FFT methods wait until a whole block is collected, adding latency equal to the block length. Setup cost, computing the FFT of the filter once, cost big O of n log n, is amortized over many blocks. If you only need one convolution, direct might be cheaper. Accuracy, FFT uses floating point complex arithmetic. Rounding errors accumulate, especially for very long blocks. Direct integer arithmetic can be exact for small integer data. Power consumption, on embedded DSPs, The FFT often uses specialized hardware and is more energy efficient than many multiply-accumulate operations of the direct method. In practice, engineers pick the smallest block size that still makes the FFT worthwhile, balancing latency, memory, and CPU load. Explanation::convolution isn't just a textbook exercise. It shows up in many everyday technologies. Number 1. FIR, finite impulse response filtering, audio equalizers, noise-canceling headphones, and biomedical signal cleaning all use FIR filters. The filter coefficients h of n describe how much of each delayed sample to keep. Convolution mixes the incoming audio with these coefficients, shaping the sound. Number 2. OFDM, orthogonal frequency division multiplexing, modern wireless standards Wi-Fi, LTE, 5G transmit data on many closely spaced carrier frequencies. At the transmitter, the data symbols are first IFFT-ED, which is a form of circular convolution to create a time domain OFDM symbol. At the receiver, a FFT demodulates it. The cyclic prefix added before transmission makes the channel act like a circular convolution, allowing simple frequency domain equalization. Number 3. Image processing, blurring, edge detection, and sharpening are done by convolving the image with small kernels, for example a 3x3 Gaussian blur. Because images are two-dimensional, the same 1D convolution formulas are applied in rows and columns or via 2D FFTs for large filters. Number 4. Radar and sonar. Matching a received echo to a known transmitted pulse uses convolution or correlation, which is a flipped version. The peak of the convolution indicates the time delay and thus distance. Number 5. Machine learning. Convolutional neural networks use learned kernels to detect features in pictures or audio. Although the kernels are small, the massive number of them makes FFT-based fast convolution attractive for large-scale training. In each case, the underlying mathematics is the same. Slide one pattern over another, multiply and add. The choice between linear and circular versions depends on how the data is stored, whether we use FFTs, and what physical constraints like the cyclic prefix in OFDM exist. Explanation: when we move from exact math to a computer, we have to think about how numbers are stored. Finite precision floating point representation - most CPUs use IEEE 75432-bit single or 64-bit double floats. These can only approximate real numbers. Tiny errors round-off appear after each arithmetic operation. Round-off buildup in FFTs - and FFT performs many butterfly operations, adds and multiplies. Each step introduces a small error. After log base 2 of n stages, these errors can accumulate. For very large n, or for filters with high dynamic range, the resulting convolution may be off by a noticeable amount. Mitigation strategies: use double precision for the FFT when the filter coefficients have a large dynamic range. Scale the input and filter so that their maximum magnitude stays well below the floating point overflow limit, approximately 3.4 times 10 to the 38 for single precision. Apply windowing or overlap save with moderate block sizes to keep the number of stages low. Memory management - the FFT needs buffers for the complex data, real and imaginary parts. Allocating large buffers repeatedly can fragment memory. A common practice is to allocate a single working buffer of size n once, and reuse it for every block. The filter's FFT can be kept in a separate read-only buffer. In place versus out of place, FFT-in place algorithms overwrite the input with the output, saving memory, but making debugging harder. Out of place keeps the original data, which is useful when the same input must be reused, for example when overlapping blocks. Integer-based convolution - for fixed-point DSPs common in embedded audio devices. Convolution is performed with integer arithmetic, and scaling shifting is used to avoid overflow. Here, rounding errors are deterministic, but must be carefully managed to prevent loss of signal fidelity. Overall, the goal is to keep the numerical error small enough that the final output sounds, looks, or behaves like the ideal mathematically exact result, while also fitting within the limited RAM and processing power of the target platform.